All right, we're getting near the end here. This is the first video on waves. I'll do a second one that includes light, sound, and the interaction of waves. In this one, we're just going to look at the difference between the transverse and the longitudinal waves, talk a little bit about the way we describe them, including things like frequency and wave velocity. First of all, waves are rhythmic disturbances. Rhythmic implies that there's some kind of timing to it, some kind of beat to it, some kind of pattern to it. If you've ever been out in the ocean, if you've ever been out in a lake in a boat, you know this. The boat rocks with a regular pattern, with a regular rhythm. Waves carry energy. This is one of the big things that you have to understand about waves. When you see a wave at the ocean, when you see a wave on a lake, you see water moving around. What we need to recognize is that that wave does not move water around. The water is displaced, but the water ends up back in its resting position again. All that moves from one place to another in the wave is energy. There are two types of waves, transverse and longitudinal. The longitudinal waves are sometimes referred to as compressional waves. So if you see these two words, they are interchangeable. The difference between a transverse and a longitudinal wave is the way that the medium moves relative to the direction that the energy moves. The difference is in the motion. In the transverse wave, the motion of those two things are perpendicular. Perpendicular means 90-degree angle. The way I always tell my students to remember that is to look at the first letter in the word transverse. It's a T, perpendicular lines. Transverse are the perpendicular type waves. The perpendicular motions that we're talking about are the displacement and the direction of travel. The way the medium moves up and down versus the way that the energy moves, in this case from left to right. The angle between those two, 90 degrees. There are several different ways we can describe these transverse waves. We can talk about their amplitude. The amplitude is the amount of displacement, or how far out of this resting position the medium moves. In this particular illustration, they have labeled it from the resting position down to one of the low points, also called a trough. It can also be measured from the resting position up to a high point, also referred to as a crest. These two measurements should be exactly the same thing. Both of these are amplitudes. We can also talk about the wavelength of our transverse wave. In this particular illustration, they have labeled it from crest to crest. It can also be labeled from trough to trough. It can be measured on the resting position as well. We can go from halfway down one wave to halfway down the next. Basic rule of thumb is as long as you're going from one point on the first wave to the exact same point on the second wave, it is a wavelength. The longitudinal or compressional waves are parallel. When we talk about the direction that the medium is moving versus the direction that the energy is moving, when we draw those lines in, when we draw those arrows in, they will be parallel lines. And the way I always tell my students to remember that is to look at the word longitudinal. Begins and ends with L's. Those are parallel lines. In this illustration, you see direction of travel. Again, this is the direction that our wave is moving. The energy is moving. We have the movement of air molecules, in this case, our medium, back and forth. Our medium is moving like this, left and right. Our wave is traveling from left to right. These arrows are parallel lines. It is a longitudinal or compressional wave. Describing these is quite different because they look quite different. We have these areas where the matter is all spread out. That is called rarefaction. This is an area of low density. This is an area of low pressure. We have these places where the medium is all crammed together. We call this a compression. This is an area of high density or high pressure. Wavelengths are kind of different. Again, it's the same general idea. One point on the first wave to the same point on the next wave, and they've measured theirs from the middle of a compression to the middle of the next compression. Easiest way I think to do it is to say that it is one complete compression, one complete refraction. That'll give you an entire wavelength. All waves have some things in common. Crests and troughs, those are unique to transverse waves. Compression, refraction, those are unique to longitudinal waves. But all waves do have amplitude. We did not draw it in on the compressional or longitudinal wave because there's no real way to draw it in. They all have wavelength. You saw that on both those illustrations. In addition to that, however, they also have frequency and wave velocity. Frequency is the number of waves per second. If you were to stand on a pier at the ocean and count the number of waves that went by and figured out how many waves passed you in a second's time, you have figured out the frequency of the waves on the ocean that day. It's measured in hertz. 1 hertz would be 1 wave per second. 20 hertz would be 20 waves per second. It can be calculated pretty easily by taking the number of waves divided by the amount of time. And again, in order to get hertz, this needs to be in seconds. So again, if you were standing on the pier and you were counting waves that went by, you counted 15 waves in 30 seconds, you would take 15 divided by 30. You'd have your frequency of your wave. Frequency is inversely related to wavelength. These two ideas are related to each other. And again, inversely related or inversely proportional means that they change in opposite ways. When one goes up, the other goes down. When the wavelength is large, the frequency is low or small. This would be a low frequency wave. When the wavelength is short, the frequency is high. You're going to get hit by a lot more waves every second. I actually got a simulation loaded up from the PHET website that will allow us to better see what we're talking about here. There's a transverse wave being generated by a wave oscillator. And what I'm going to do is I'm going to increase the frequency. And what we need to do is see what happens to the wavelength. See what happens to how long those waves are. I'll move the frequency way up. And you'll see those wavelengths got shorter. Higher frequency, shorter or lower wavelength. I'll dump that frequency way down. And when that frequency is low, these wavelengths stretch way out, so much that you only have part of a wave on the screen. And kind of in the middle, you can see the wavelength. Jam it way up, and you see that wavelength shrunk way down. High frequency, small wavelength. I'll reduce that frequency to a lower value, and again, when that frequency gets low, those waves get really long. Low frequency, long wavelength, high frequency, short wavelength. Frequency is also related to something called period. Period is the amount of time it takes for one wave to pass. Frequency is waves per second. Period is seconds per wave. They're inverse of each other. They're inversely related. High frequencies mean short periods. If you get a lot of waves hitting you every second, that means it takes very little time for one wave to hit. I think it's kind of common sense, but you do need to know it, so worth mentioning. Wave velocity is the speed of the energy in the wave. Remember, the matter doesn't go from one place to another. It is energy that goes from one place to another. Wave velocity is calculated by taking your wavelength times your frequency. This will be measured in meters. This will be measured in hertz. So if you see a question like this, if a wave has a wavelength of 5 meters and a frequency of 20 hertz, it asks you for the wave velocity. We will take our wavelength, multiply it by our frequency, and that will give us our velocity 5 times 20, 100. Unit for velocity, whenever you have meters and hertz, will be meters per second. So we can say that the energy is moving 100 meters per second in this particular wave. Again, just wavelength times frequency. You could do it with a speed equation, but in many cases, some of these waves just move way too fast and there's no way to use distance and time. That equation works better. The amount of energy in a wave depends on several factors, including amplitude, frequency, and wavelength. The greater the amplitude, the greater the energy that wave carries. The shorter the wavelength, the greater the energy it carries. And finally, the higher the frequency, the faster those waves hit you, the greater the energy they have. Obviously, the inverses would also be true. If you had a lower amplitude, it would be less energy. If you had longer wavelength, it would be less energy. If you had lower frequency, it would be less energy. That is it for this one. Look for the video on light, sound, and the interaction of waves to come next.